Hi, this is John Whitaker, and this is, I'm here for the Probability 1 graduate level class, and this is our 13th video lecture. And at the end of our 12th video lecture, we had come up with an expression for the sum of independent continuous random variables. And here's what we had. There are continuous random variables that are independent. Then the PDF probability density function of x plus y is alpha of x plus y. We'll say acting on A, and it's equal to the interval from minus infinity to infinity of f sub y, and then it was times f sub x of A minus y, and then it's dy here. Dy. That's what we got. Okay, so I'm going to do an example where we use this. And so let's let x plus y be uniformly distributed random variables. And let's make them be over 0 to 1. Okay. And suppose x plus y are independent. And what we're going to be charged to do, our directions, are going to be to find the PDF of x plus y. Well, here by our formula, we should note that f of x plus y due to independence is equal to, it is going to be the integral from minus infinity to infinity of f sub y of y, f sub x, the PDF of x, evaluated a minus y, and then dy. That's what we have. Okay. Now, one thing that we should recall is that uniformly distributed random variable, that's going to mean that f sub x of c equals to f sub y of c, and that's either going to be, because we're talking about it being defined over 0 to 1, it's 1 over 1 minus 0, which is just 1, if c is an element from 0 to 1, and it's 0 otherwise. So, what we have then is that the PDF of x plus y, evaluated today, okay, look, this f sub y of y, it's going to be, remember we're integrating with respect to y, it's going to be 0 most of the time. And the only time it isn't 0 is when y is in between 0 and 1. 0 and 1. When y is in between 0 and 1, f sub y is 1. So we just have remaining f sub x of a minus y dy. I want to talk about the values of a next. And so here's what I want to tell you. Note, since the x values is between 0 and 1, and the same for the y values, then a, which is going to be the result of x plus y, has to be between 0 and 2. Okay. For where the PDF would be non-zero. Okay, and so for that integral to be non-zero, for f of x plus y of a to be non-zero, what we're integrating needs to be non-zero. That says that f of x of a minus y has to be different from 0. And that occurs when a minus y is sandwiched in between 0 and 1. Because remember, the PDF of x is defined to be non-zero only when what we're evaluating at is in between 0 and 1. So here if we solve for y, we want, if you will, okay, this says that minus a be less than minus y be less than 1 minus a divided, so we want to look at, we divide by minus 1. We want to look at, I think it's a minus 1 less than or equal to y less than or equal to a. Now, when we look at this region where f of x plus y is going to be non-zero, what we're integrating here is to be non-zero. If we think of this as the y-axis, and this is the a-axis, okay? The y values run up from 0 to 1. The a values run from 0 to 2. That's what we have. Now, when I look at here, so solve for a, this bottom one says a is equal to y minus 1, if you will. Okay. I'm sorry, y plus 1. So here, it starts off when y is 0, you get 1, y is 1, you get 2, so it looks like this. And here, y equal to a, or a equal to y, this other part, that's this diagonal. It has 0, 0, and 1, 1 on it. So when we look in this region, and we talk about doing this integral, what we notice is that what we're going to be integrating, this quantity right here, it varies, the integration with respect to y. It's going to vary depending upon what a is. For instance, if a is in between 0 and 1, the y values run from this line to this line. But if a is between 1 and 2, the y values run from this line to this line. Okay? So what we're going to have to do is we're going to have to break up our answer for the PDF of x plus y depending on whether a is between 0 and 1 or between 1 and 2. So here, if a is sandwiched in between 1 and 0, then f sub x plus y of a be equal to the integral. Okay, so here I know that it's going to be f sub x of a minus y, but that region where we're integrating is here, where we have y is in between these two regions. You can check that by just picking a point from this region to see that it satisfies this. Okay, well, what we're going to have to do is, if a is between 0 and 1, the y values are going to run from 0 to here, they're going to run to this line, that was a. And here, we're going to have the f of x, the f sub x of a minus y, which is what we're integrating, it's just going to be 1, and then dy. So we end up getting y evaluated from 0 to a, that's equal to a. Okay. Now, before I move over, for a fixed a in between 1 and 2, that's what we're going to consider now. The y values will run from this line, which is a minus 1, to this line, which is y equal to 1. So I'll write that down next. So if a is between 1 and 2, then f sub as I said, it's going to be the integral. The smallest y values are a minus 1, and the biggest y values are 1 of 1 dy. So this ends up being y evaluated from a minus 1 to 1. That's equal to 1 minus the quantity a minus 1. That equals to 2 minus a. So what we get is that f of x plus y of a is going to be equal to, for these independent, uniformly distributed random variables on 0 to 1, it's going to be equal to 0 if a is less than 0. It's going to be equal to, it was a if 0 is less than a is less than or equal to 1. Then it's going to be equal to 2 minus a if 1 is less than a. It could be 1 or less than or equal to here. With less than or equal to 2. And then it's going to be 0 if a is greater than 2. And so that's what we have for the PDF. Now, one thing I want to point out about this example is that when you added two uniformly distributed random variables that were independent, you did not get a uniformly distributed random variable. Okay? This is not uniformly distributed. But a lot of times when you add certain types of, the same types of random variables added, when you add them together, what you get is the addition is that same type of random variable. And I want to write up some facts about that. Really 3 of them, one of which I'll prove. Okay. So here is a fact. If x and y are independent Poisson random variables with parameters lambda 1 and lambda 2, then x plus y is Poisson with parameters with parameter lambda 1 plus lambda 2. Okay. So we want to prove this fact. Now, one thing I want to tell you is that we had a result about the PDF of x plus y when we had independent continuous random variables. But Poisson random variables are discrete, so they don't fit that case. So what I'm going to do is I'm going to look at, well, we'll start off by assuming the conditions. So let x and y be Poisson with parameters lambda 1 and lambda 2. And I got just a x and y are independent. Okay. Okay. Then, f of x plus y, the PDF of x plus y, evaluate a. What that's equal to is the probability that x plus y is equal to a. Okay. And what that's equal to is the probability of a union of sets. It's the union that x is equal to let's say, k, and y is equal to a minus k, where k would run from 1 to a. Okay, so that's how they can add up to give you a. X is k and y is a minus k. And so, if you look at a particular k, let's say k equal to 3, when x is equal to 3 and y is equal to a minus 3, and you look at another k value, let's say when k is 4, x is equal to 4 and y is equal to a minus 4, those events can't happen simultaneously. So they're independent, they're mutually exclusive events. And so we're uniting those up. So that's equal to the probability of, that's equal to the sum, I should say, as k runs from here. Let's say, I think I should have started at 0. Yes. K runs from 0 to a of the probability that x is equal to k and y is equal to a minus k. That's the sum of those things. Now we have independence between x and y, so that's equal to the sum as k runs from 0 to a of the probability that x is equal to k times the probability that y is equal to a minus k. And now, don't forget that we have Poisson parameter variables, so we get the that these probabilities involve their PMF, so it's the sum as k runs from 0 to a, and for Poisson here, this is going to be e to the minus lambda 1 to the k, all over k factorial, and here this is going to be e to the minus lambda 2 to the k, all over k, it should be a minus k, not k. Here's a minus k factorial. That's what the power is there. Okay, excellent. Now, that could be rewritten, combining terms in the sum. K runs from 0 to a. Here, this will be e to the minus lambda 1 plus lambda 2. And then we have lambda sub 1 to the k, lambda sub 1 to the a minus k, all over k factorial, and then a minus k factorial. Okay. Now, what I want to tell you, or have you observe, is that we can pull out this e to the minus quantity lambda 1 plus lambda 2 because it doesn't depend on k. Okay. Now, here we have a sum as k runs from 0 to a. And I'm going to put lambda sub 1 raised to k, and the lambda, this should then 2, lambda sub 2 raised to a minus k. And here, this part looks like the denominator of a choosing. And what it really could be thought of is a choose k if we had an a factorial on top. So I'm going to put an a factorial, and then I'm going to have k factorial times a minus k still existing in the bottom. Okay. But I can't just insert that a factorial without compensating, so I need a 1 over a factorial in the bottom. But I can have an a factorial and 1 over a factorial in and outside because it does, that quantity doesn't depend on the index k. So this is e to the minus lambda 1 plus lambda 2 over a factorial. And here, this is the sum as k runs from 0 to a of a choose k, lambda sub 1 to the k, lambda sub 2 to the a minus k. And this you can apply the binomial theorem to get the following result. That's going to be equal to e to the minus lambda 1 plus lambda 2 all over a factorial. And then using the binomial theorem, here what we're going to have is lambda sub 1 plus lambda sub 2 to the a. Okay. And that is nothing more. This is, okay, so f sub x plus y evaluated at a is this quantity. Lambda 1 plus lambda 2 over a factorial lambda 1 plus lambda 2 to the a. And I want you to recognize that that is the, here where I should say something, a could be equal to 0, 1, 2, forever. That is the PMF for a Poisson random variable with parameter lambda 1 plus lambda 2. Okay. So we get to make our conclusion. With parameter lambda 1 plus lambda 2. Remember, that's how we define the Poisson random variable. It has this PMF. Well, I'm going to write up some similar facts about some other discrete random variables, but I will prove them. Not necessarily discrete, but random variables. So in particular, as a facts, if x and y are independent this is the first fact, binomial random variables with parameters, binomial have two parameters. How many times you did the experiment? So let's say the first one is m and p, that's probability of success, and the other random variable y has parameters n and p, so they both have probability of success being p. Then x plus y is binomial with parameters m plus n and p. That's what we have. And secondly, if x and y are independent normally distributed random variables with parameters, for each one of them they have two, mu sub 1 and sigma squared, sigma sub 1 squared, and let's say mu sub 2 and sigma sub 2 squared. Then x plus y is normally distributed with parameters mu1 plus mu2 and sigma sub 1 squared plus sigma sub 2 squared. So that's the fact that I wanted to list. The next thing I want to talk about, and it'll be what we talk about for the remainder of this lecture, is about something called moment generating functions. So here's its definition. So the moment generating function for a random variable x is a function. Okay. Sometimes I'll label this phi sub x of t, okay, that is given by phi sub x of t is equal to is the expected value of e raised to the tx. Okay, and that I'll expand upon depending upon whether x is discrete or continuous. Note, phi sub x of t is equal to, it's the sum over all the x values, output values, of e tx f of x, where f of x is PMF. If x is discrete, and it equals to the integral from minus infinity to infinity of e t dx f of x dx if x is continuous. Okay, the reason that we study this particular function is because of one main fact, and we'll get to it in a piecewise fashion. The first time, first I'll look at the fact that says, note, oh, there's one other thing I want to say. We assume phi sub x of t is defined, or can be defined, over some interval minus h to h containing 0. Might be defined for more than that, but here we at least can get it over that region. Okay, so here's the intermediate fact that we want about the moment generating function. Well, here's what it is. The nth derivative of the moment generating function, okay, and that's with respect to t, is equal to the expected value of x sub n times e sub x, e sub tx. Proof's very straightforward. It's a proof by induction. So first of all, when n is equal to 1, then phi prime of t, which is really the derivative with respect to t, phi of t, which would be equal to the derivative with respect to t of the expected value of e to the tx, which is equal to, now I'm not saying y, but you can pull this derivative inside this integral or sum. So that's going to be the expected value of the derivative with respect to t of e to the tx, which will be equal to the expected value. So we take this derivative, this would be, remember we're taking the derivative with respect to t, so it's x times e to the tx, and that is what we wanted to show in the case when n is not 0, but 1. Sorry, made a mistake. So the statement is true when n is equal to 1. Okay, so by induction, the next step is to assume the statement is true when n is equal to k. That is, that the kth derivative of t is equal to e, the expected value of x to the k times e to the tx. Okay. We must show the statement is true for k n equal to k plus 1. That is, we must show the k plus 1 derivative of phi is equal to the expected value of x to the k plus 1 e to the tx. Okay. Well, note the k plus 1 derivative of t is really the derivative with respect to t of the kth derivative of phi, long generating function, and that's equal to the derivative with respect to t. We know what this is by our induction hypothesis. That's the expected value of x raised to the k e to the tx and that's going to be equal to, again, we pull in the derivative inside the expected value. That's the derivative with respect to t of x raised to the k e to the tx. This x to the k is a constant with respect to t, so this becomes the expected value. If you write down the constant times the derivative of e to the tx, that's e to the something. The derivative of e to something is e to the something times the derivative of something, which would be with respect to t, which would be x. So that's equal to the expected value of x raised to the k plus 1 times e to the tx, and that's what we wanted to show. Okay. And so the statement is true. Now the main fact is the following. That the moment generating function of x, if you take its nth derivative and evaluate that to 0, what you get is the expected value of x to the n. Okay, this is called the nth moment of x. And this proof is not so bad to do, especially from the previous fact. In particular, here's what we see. We note the nth derivative of the moment generating function with respect to t is equal to the expected value of x of n e to the tx. That's by the previous fact. So, if you were to evaluate this at 0, what you get is the expected value of x to n times e to the 0 times x, which is just equal to the expected value of x of n, and then 0 times, the random variable 0 times x is just 0. This is e to the 0, which is just 1. And so we just get the expected value of x to n. That's it. Now I want to do examples of finding the moment generating function for some particular random variables. And so we'll start off with a binomial random variable. So we'll let x be a binomial random variable with parameters n and p. Then the moment generating function, so we abbreviate, let me write it down one more time. Moment generating function, we abbreviate that MGF phi sub t, phi of t, phi sub x of t is going to be equal to, okay, so here's what it is. It's p times e to the t plus 1 minus p, and all that raised to the n. Let's prove that. So this is a computation, as many of the proofs are for us in probability. Okay, so here's the proof. Again, we're letting x be binomial with parameters n and p. Then the expected value, phi of t is going to be equal to the expected value of e raised to the tx, which is going to be equal to, now this is binomial, so we're going to have a sum, and here the x values can be 0 up to n, and it's the number of successes in these trials, of e raised to the tx, and then we want f of x, the PMF of the binomial, which was n choose x, p to the x, 1 minus p to the n minus x. Okay, that's what we have. Okay, and then the next thing that I would do is notice that this is equal to a sum. So it's a sum as x runs from 0 to n. Here, this is e to the t raised to the x. That's what you do, you multiply the exponents in that situation. So I'll rewrite this as n choose x, and then I'll say it's e to the t times p, all that raised to the x, times 1 minus p to the n minus x. And then using the binomial theorem, this is really equal to e to the t times p plus 1 minus p raised to the n. And that's what we said we would get. That's its proof. And then we should check something. What we should do is we should check that if we differentiate this one time with respect to t, we get the expected value of a binomial, which was np. And if we differentiate it twice, that will help us find the variance. So I'll do that. So just as an observation, when x is binomial, with parameters n and p, we have p sub x of t equal to that e sub t times p plus 1 minus p raised to the n. Okay. So if we take this first derivative with respect to t, what we're going to get is n times, using the chain rule. Really, we're using the power rule extension of the chain rule. E to the t times p plus 1 minus p to the n minus 1. Then you have to take the derivative of what was being raised to the power with respect to t. So that's going to be times e to the tp. And here this is going to be 0. When I evaluate that at t equal to 0, this is going to be n. Here this is going to be 1. So it's p plus 1 minus p. Raised to the n minus 1, e to the 0 is 1 again, so times p. This is p minus p is 1, I'm sorry, 0, you add 1 to it, you get 1, 1 raised to the power of 1, so this ends up being np, and that's what we thought. So that is the expected value of x. And then, note the second derivative with respect to t, so I'm looking here. This is going to be n, so I'm going to write down the first. E to the tp, I'm using the product rule, plus 1 minus p to the n minus 1. Now I take the derivative of this guy, which is e to the t times p itself, plus, here I take the derivative of this first part, which is n times n minus 1, e to the tp plus 1 minus p to the n minus 2, and just write down the second, which is e to the tp. That's what we have. So when you take the second derivative and evaluate that at 0, the monk generating function, here again, this is going to be n times p. I'm sorry, this was plus, not equals. Here this is going to be plus n times n minus 1. This is 1, and so we just get p here. And so that's equal to, this is np. You know, I've made a mistake. This should be squared in the derivative. So I made a mistake in the derivative. I'm looking right here to take its derivative. It's a product. You write down the first. I did. Take the derivative second. There it is. The derivative second is itself in this case. Now you write down the second. That's e to the tp. Now you take the derivative of this first. So it's n. That's constant. You bring down the n minus 1. E to the tp plus 1 minus p to 1 less power. And then you have to take the derivative of this, which is e to the t times p. So we get e to the t times p to be squared. And so here, this should have been a p squared here. And, I'm sorry, should have been a p squared here. Okay? That's np plus n squared p squared, and then minus np squared. That's what we get. That's the expected value of x squared. Let me make sure that my work is correct there. Okay, so it's np, yes, that is right. All right, so finally, we get the variance of x, which you'll remember is the expected value of x squared minus the expected value of x to b squared. That's equal to, so here it's np plus n squared p squared minus np squared minus, this was n squared p squared when you square it. So if this guy and this guy cancel with each other, we're left with np minus np squared. You can take out an np and you have 1 minus p. That's exactly what the variance was for a binomial. Okay? That's good. I'd also like to look at a fact about a Poisson random variable. So if x is a Poisson random variable, with parameter lambda, Remember, lambda has to be positive. Then the moment generating function of x is, I'll write it over here, it's phi of t equal to e to the lambda e to the t minus 1 in this way. All right, piece of x. Here's the proof. We're going to let x be Poisson with parameter lambda. Then phi of t, the moment generating function, remember it's the expected value of e to the tx, which will be equal to the expected value of, the sum of e to the t x, f of x, and so that's e to the minus lambda, lambda to the x all over x factorial. Here x runs from 0 to infinity. This can be rewritten as the sum as x runs from 0 to infinity. This will be e to the minus lambda. Here, you can rewrite this as e to the t times lambda, all that raised to the x, over x factorial. That, you can bring out the e to the minus lambda. Here you have the sum as x goes from 0 to infinity. E to the t lambda, all that raised to the x over x factorial. This is the summation part, is the Taylor series expansion for e to some quantity. As a matter of fact, it's e to this quantity, e to the t lambda. And so we can add these exponents, and I get e to the e to the t times lambda minus lambda, which we can factor out lambda and get e to the lambda times e to the t. It would be minus 1, and that's what we said it would be. So that's its proof. Again, a computational proof. And let's check the expected value and the variance of a Poisson random variable. Remember, both times they were lambda. Using the moment generating function, and then we'll call it quits for this lecture. So note, if we take phi of x prime of t, what that's going to be equal to, so it's going to be e to the derivative of something, it's e to the something, times the derivative of something. So the derivative of the power here is going to be lambda e to the t. And so if we evaluate that at 0 for the t value, this is e to the, this would be lambda, this is e to the 0, which is 1, 1 minus 1 is 0, multiplying here, and then this is lambda e to the 0, this is 1, lambda 1, which equals to lambda, which is what we said we would get for the expected value of x. And then if we look at calculating the expected value of the quantity x squared, we take the derivative of the moment generated, the second derivative. And so I'm taking the derivative of the first derivative. I have to use the product rule. That's e to the lambda. I'm writing down the first. I got to take the derivative of the second. That is itself, lambda e to the t in this case. Now, we're going to have plus. And again, we write down the second. So it's lambda e to the t. And I take the derivative first, which is e to the something derivative. So e to the something times the derivative of something, that's the derivative of lambda times the quantity e to the t minus 1. But that's just lambda e to the t, so I'm going to put a square here. So that says that the second derivative, evaluated at 0, let's see, that's going to be 1, that's a lambda. Okay? Here, this is 1 times lambda to the b squared, so it's plus lambda squared, and this was 1. So we get lambda plus lambda squared, and indeed that was the expected value of x to b squared. But just to be complete here, what we get for the variance. The variance of x when it's croissant is going to be the expected value of x squared minus the expected value of x. And so here we're getting lambda plus lambda squared minus, oops, I made a mistake, this is to be squared. And the expected value of x we found to be lambda, so it's lambda squared, so we just get lambda. And that's what we were expecting. Okay, ladies and gentlemen, that's enough for this video lecture. Thank you very much.